So welcome to exam 2 review for calculus 2. So we start with approximate the integral using n equals to 4. And the integral is the integral from 1 to 2 of the square root of the function x squared minus 1 with respect to x. They're using trapezoidal rule. So the things we need to see and remember here is that n equals to 4. These are the strips. For this case, we have n equals to 4. We have the interval AB is from 1 to 2. We have the function f of x is equals to the square root of x squared minus 1. So with all these, we start by finding the length of each, or the length or the width, and it's given by b minus a divided by n. So we have 2 minus 1 divided by the number of strips or rectangles or the n, which is 1 over 4. So after we find the length, we find the grid points. So by finding the grid points, it's easier to draw like the interval from 1 and 2. So we're starting at 1 and then we end at 2. And because the length is 1 over 4, I can write this one in terms of 4. So this one is 4 over 4. And the last one, this 2, is 8 over 4. So meaning that I'll be moving 1 over 4 from each and every one of them. So 4 plus 1 is 5 over 4. The next will be 6 over 4 because I'm adding 1 over 4. From 6 over 4 is 7 over 4 because they are evenly spaced, 7 over 4, then 8 over 4, which is 2. Now I have all what I need. Now from there, to use the trapezoid rule, if you have to draw a trapezium, in the first one, you need to find all the function values. So find the function values. And that I mean find f at the first one of over 4. So you substitute 1 in the integrand. So 1 squared minus 1. So that's 1 minus 1, 0. F at 5 over 4. So you get square root of 5 over 4, which is 25 over 16, minus 1 is 16 over 16. So you get 9 over 16 in the square root, and that becomes 3 over 4. We find f at 6 over 4, which is square root of 36 over 16, minus 16 over 16 again. That becomes 20 over 16, and the square root that becomes 2 root 5 over 4. F at 7 over 4, it's 49 over 16, minus 16 over 16, or 1, which is 33 over 16, which is root of 33 over 4. And the last one is f at 8 over 4, or f at 2. Let's use 2. So we have square root of 2 squared minus 1, which is square root of 3. So we have all the function values. So we take a typical trapezium. If you have to do trapezium on each interval, so the first interval, we'll use the first trapezium. If I was to draw a trapezium, let me say, for example, here, I would use this height. It's a trapezium, draw a height, and then that's my first trapezium. The other trapezium we will share a side. Another trapezium, for example. Let me say another trapezium if it was to be drawn like that, and maybe another trapezium. I'm just drawing like examples, another trapezium of that form. That means that the sides which are inside are shared, but the ones which are starting are not shared. So if I was to find the area enclosed by the first trapezium, I would say the first one, that is f at 1, plus f at 5 over 4, I'll divide by 2. That's 2 parallel sides times the height. This height is 1/4. Plus the second one, I'll take the height, which is shared 5/4, f at 5/4, plus f at 6/4. Then I'll divide by 2. Then I multiply by the perpendicular distance, plus the other one is f at, I'm now in that trapezium. So I'm having a height share, that's 6/4, plus f at 7/4. Again, divide by 2. You multiply by the distance or the length. And the last trapezium will be f at this one, 7/4, plus f at 8/4, or f at 2, divided by 2, multiply by the distance or the length. So this is the area which can be approximated using the trapezoidal rule. So we find that f at 1 and f at 2, they're not shared. So I can take f of 1/2 plus the last one, f at 2/2, but all the others, it's f at 5/4/2, f at 5/4/2, that's f at 5/4. The middle ones, they'll be shared. So we'll be having f at 6/4, then f at 7/4. And then after I add all of them, I multiply by the length, and the length was 1/4. So if you substitute all the function values in this function, you find that answer, and then you multiply by 1/4. After you substitute them, you find the answer as 1.0426. That's the answer that approximates the area. For the Simpson's rule, we will remember, again, what we have n equals to 4. We have that the bounded interval 0 to pi, and we have the function or the integrand f of x as x cosine of x. So again, the length, find the length first. Length, it's b minus a, that's pi minus 0 divided by 4, that's pi/4. So we can draw to find the grid points, we can draw that interval 0 to pi, and then because it's pi/4, I can write the last pi as 4/4 pi. And that means from 0, I'll be moving pi/4 because of the uniform length, 2 pi/4, then 3 pi/4, and then finally 4/4. For the Simpson rule, I can index this as the start one, f at 0, f at 1, f at 2, f at 3, and the last one, f at 4. And the formula for the Simpson rule, it's called Haddad-Simpson's rule. Let me write Haddad here to remind you. I'll take the area, approximate the area. I'm going to say area is approximated by, you take the length of each interval, divide by 3, because it's Haddad-Simpson rule. Then the first one, function value, plus the last one, in this case is the fourth one, plus twice the ones in the even position, that even position is index 2, plus 4 times the ones in the odd position, and that position is f at 1 plus f at 3. So this is what we will do. First of all, let's find the function value. Function values. So the first one, f0, or f at x equals to 0, it's 0 times cosine of 0, which is just equal 0 times 1, which is equals to 0. The other one is f at pi/4, the second one, which is pi/4 multiplied by cosine of pi/4. And if you remember the 30, 60, 90, and 45, 45, 90 angles, we have that this is pi over 4. And cosine of pi over 4, it's 1 over root 2. Then the other one is f as 2 pi over 4. That is 2 pi over 4 is pi over 2. Then cosine of pi over 2. Cosine of pi over 2 is cosine of 90. So it's pi over 2 times cosine of 90, it's 0. The other one is f at 3 pi over 4, which is 3 pi over 4 when you substitute in the x value times cosine of 3 pi over 4. 3 pi over 4, in terms of degrees, it's 135. And 135 degrees is in the second quadrant. Second quadrant, in maths, we all know that cosine is negative. So it's just 3 pi over 4. And cosine is negative, but the reference angle should be 180 minus 135, which is 45. So it's still 1 over root 2, but with a minus sign. The other one is f at pi of 4 over 4, which is equals to pi multiplied by cosine of pi. Again, you get pi, but cosine of pi, that's cosine of 180, and that is minus 1 because in the second quadrant. So these are the function values. So what we do to get the answer for the area approximation using Simpson rule, we just substitute them. And the indexing here, I can just say 0, 1, 2, 3, and the last one 4. So I'll be having the length pi over 4 divided by 3, and then the first one and the last one, is just minus pi plus twice the second one in the with the index 2, which is just 0. This is the index 2. I just wrote them here as I was listing them. Plus 4. The ones in the on position, it's pi over 4 times 1 over root 2. That's pi over 4 root 2. The other one in the odd position is in the third one, it's minus 3 pi over 4 root 2. Then a big bracket. So the area approximation here should be pi over 12 minus pi. This is 0. Plus, this 4 will cancel with all the 4's in the denominator. So you get pi over root 2 minus 3 pi over root 2. That's just minus 2 pi over root 2. You can continue simplifying further to get pi over 12 minus pi, and then we can have minus, rationalizing minus 2 root 2, you get minus 2 root 2 over root 2 times root 2, and 2 will cancel, you get minus root 2 pi. And you can factor out the pi, you get pi squared, and then you can just leave the answer in this form. The third one, it's midpoint rule. So for the midpoint, again, we have n here equals to 5. We have the interval AB equals to 5 to 10. And the integrand of the function f of x equals to x power 5 ln of x. So the first thing, we find the length. And the length here, we can denote it as del x equals to b minus a divided by n, which is 10 minus 5 divided by 5, which is equals to 1. So the spacing is 1 apart. So now to know the grid points, we draw the interval from 5 to 10, and 1 apart we move to 6, uniformly 7, 8, 9, and 10. And because we want the midpoint, so the point in the mid will be the point there in the dotted in those cross dots. So that means that the point between 5 and 6 will be my first point, and that will be, I'll be finding the function value f at 5.5. The other one is f at 6.5. Keep on adding 1. F at 7.5. Function when x equals to 8.5. And the last one is the function when x equals to 9.5. So substitute them in the function x power 5. So x is 5.5 for the first one. Raised to the power of 5. We find then ln of 5.5. And then you complete all of them, plugging in the value of x. And then after that, the midpoint answer area of this integral will be approximated by, you add all the heights or the function values. F at 7.5 plus f at 8.5, f at 9.5. Once you add all of them, you multiply by the length or the spacing, which you got. In this case, you got 1. And that's the answer that you get using the midpoint rule. So let's do number 4. Which integrals are improper? To know integrals are improper, you need to know 2 things. One, they may be having infinite intervals. And we have 3 types of infinite intervals. The one with a onwards to infinity, maybe the one with minus infinity all the way up to b. A and b are dummy variables, or maybe from minus infinity to infinity. That's the first case. Second case is that you can have some infinite discontinuities inside the interval, calling the infinite discontinuities. Or unbounded intervals. So the first one is from 0 to pi over 4 tan of x with respect to x. So when we draw a function of tan, this function will be continuous from 0 to pi over 4. So this one is proper. But the same function tan of x from 0 to pi over 4, when we draw the function of tan, we find that when x equals to, at x equals to pi over 2, we have what we call a vertical asymptote. So that means that at x equals pi over 2, this function will break, and that means that it has an infinite discontinuity at pi over 2. So meaning that this one is improper integral. And the reason is the second one here. Reason infinite discontinuity. Be specific, it has a vertical asymptote at x equals pi over 2. The third one, to check or to show, to see this, I can simplify or factor out x in the denominator to get x squared, to get x minus 1. And then we find that this function, it's not continuous at some points here, because at x equals to 1, if you are to check at x equals to 1, this function will break, and also at x equals to 0. So this function, again, it has infinite discontinuities. Continuities. The last one, we can see that one it has infinite interval. So again, it's improper. Of the type A infinity. So let's evaluate the integral here. And before we do the evaluating of this integral, we ought to see that using the fundamental theorem of calculus, so using the fundamental theorem of calculus, that's a fundamental theorem 2 of calculus, we say that we need to have a function to be continuous on the interval from 0 to 5. So we check, but this function, if you were to substitute x with 0, it's not continuous. So that means it's improper. So we ought to then find this integral using the limit. So this is the same as now using the limit. And I can say as, let's say A approaches 0 from the right side, and then we have, where you have 0, you put an A to 5 of the function dx over 2 root x. So this is the same. I'll keep on moving the limit as A approaches 0 from the right side. The integral from A to 5. Then this is, I can factor out a half, and I'll be having x power minus a half with respect to x. So this is the same as a half limit as A approaches 0 from the positive side. The integral, you add 1 to the power, so you get a half. Then you divide by the new power, a half. Then the limits of integration is from A to 5. So again, a half can be factored out, but because I'm dividing, it's like I'm multiplying by 2. So I'll be having a half times 2. Then limit as A approaches 0 from the right side of root of x. So this will cancel with that 2. So you have that, and then we have A and 5. So substituting the A, you have this as the limit as A approaches 0 from the right-hand side. And then we have root of 5 minus root of A. And this we can solve to get that answer becomes, if you're approaching A from the positive side of 0, so that means that all the numbers will be positive, and that means the answer here for this case will be, root 5. As you approach 0. So let's do number 6. So this can be splitted into 2, minus infinity to 0 dx over 1 plus x squared plus from 0 to infinity dx over 1 plus x squared. And then we use the limit as, let's say, A approaches minus infinity of the integral from A to 0 plus limit as B approaches infinity 0 to B. So, and when we do the integral here, this one is a special one. We know as A approaches minus infinity, the integral here becomes arctan x, and the limit is from a onwards to 0. And the other part, same thing, we have limit as b approaches 0 in infinity, arctan again of x. And you have the limit here from 0 to b. So this will become limit as a approaches minus infinity, arctan of 0 minus arctan of a plus limit as b approaches infinity, arctan of b minus arctan of 0. So arctan of 0 is 0. So you have this part as limit as a approaches minus infinity minus arctan of a plus, again, parentheses, this one will go to 0 also. You have limit as b approaches 0, infinity, arctan of b. So, and as a approaches minus infinity, you find that arctan will become minus pi over 2. And also as b approaches infinity, arctan b will become pi over 2. And this will become pi. So consider parametric curve x equals t to the power 5 and y equals ln of t for t equals t greater than 0. Then we find equation in x and y for the curve. So we have x equals t to the power of 5. And we have y equals to natural log of t. So to write this equation in terms of x and y, it's easier to change y any. You can change any, but let's change y equals ln of t. And ln, the inverse function of ln of t is exponential to the power of t. So I will multiply by exponential. For this part, I get exponential power y equals to exponential, then power ln of t. So this will give you exponential to the power of y equals to exponential ln. So we get t on this side. Then we have x equals to t to the power of 5. So where we have t, we substitute with exponential power 5. We have x equals to exponential power y, and then times 5. By the properties of the indices, we get that this is 5 times y. So we can leave it in terms of that, or we can just have y equals 2 by just again introducing natural log on both sides. Both sides. This we have ln of x equals to 5y ln of e, and ln of e is 1. So that will give you ln of x equals to 5y. If you divide by 5 on both sides, we get that y equals to 1 over 5 ln of x. For number 8, find the equation of tangent to the curve. Tangent to the curve. Find the equation of tangent line. So there's a word tangent. There's a word line here. Find the equation of tangent line to the curve at the given point. 5, 6. So we have 5, 6. So we can call this one x1 and y1. So, and the equation of a tangent line is always given as y equals to mx plus b. So what we need to find is m. And to find m, we need to find the derivative. So we find dy dx. And in this case, we have dy with respect to t. Then we divide here dx with respect to t. So dy dt is just equals to 2t. That's a derivative. Then dx dt is derivative, which is 1 over t. So this one simplifies to 2t squared. Now we need to know the value of t. So x equals to 5 plus ln of t. That means that when in this case, x at this point, x is 5. So it's 5 equals to 5 plus ln of t. So that means we can subtract 5 to get 0 equals to ln of t. To get t, we use exponential. So exponential to the power of 0 equals to t. So t equals to 1. Again, we can confirm that by y equals to t squared plus 5, because when in this case y equals to t squared plus 5, y is 6 equals to t squared plus 5. So then we solve for t to get t squared, and this side we get 1. So that means that t equals to plus or minus 1. But because you are looking for time, t is positive. So here we could have gotten t equals to plus or minus 1. We neglect minus 1, so t equals to 1. So this means that dy dx at t equals to 1 is given as 2. Then you plug in 1 for t. So you get answer is 2. So the slope is equals to 2. And because we wanted the equation, let me put it here. We get y minus the y1, 6 equals to m, which is 2 in this case, x minus x1, which is 5. So that means we have y equals to 2x minus 10, and then we move 6 on the other side. So we have that the equation is y equals to 2x minus 4. That's the equation of tangent line at that point. So I find rectangular equation for the polar equation. R equals to 4 cosine of theta, and identify the figure. So all the time we see R equals to 4 cosine of theta, we need to remember how we represent R and theta. So to get R, so we need to find R. So we know that x squared plus y squared equals to R squared. So that means that to go to polar coordinates, to go to rectangular coordinates, I need to have this form in my mind. And the other one is x equals to r cosine of theta, and y equals to r sine of theta. So we have r equals to 4 cosine of theta. So what we do, we multiply by r across. So we get r equals to 4 cosine of theta. We multiply everywhere by r. So this will result to r squared equals to 4 times r cosine of theta. That way we have all what we want, because we have r squared, it's x squared plus y squared equals to 4. And the r cosine of theta is known as x, or we know it's x. So we have x squared plus y squared equals to 4x. So we can move 4x on the right-hand side. We get minus 4x plus y squared equals to 0. And then we complete the square. So we have x squared minus 4x. So we add a half the coefficient of b. And whatever we do on the right-hand side, we do it on the left-hand side. So it's 0 plus the same thing, minus 4 over 2. This is 4 over 2 squared. That's called completing square. So that will give you the right-hand side x minus 4 over 2 squared. That's what x minus 2 squared. You observe that now the whole of this part, it's the same representation as this, plus y squared equals to minus 4 over 2 squared. That's 4, or just 2 squared. And this equation is an equation of the form x minus a squared plus y minus b squared equals to r squared. And this equation of a circle, general equation of a circle, with the center AB and radius r. So in that case, our equation A is 2, B is 0, and our r equals to 2. Finally, find the area enclosed by one loop of the four leaved rows r equals to cosine of theta, cosine of 2 theta. So we don't have to draw, but we know r equals cosine of 2 theta. To be a loop, that means that to get the limits of integration, I'll set this one to 0. And then I'll have 2 theta equals to cos inverse of 0, or arc cosine of 0. And we get 0 on a unit circle at pi over 2, and can say n minus pi over 2. Then we want to find this now theta, 2 theta. So theta equals to pi over 4 and minus pi over 4. So to find the area enclosed by one loop, we do integral from alpha to beta, a half r squared d theta. And this is, you can factor out a half, so you do the integral from minus pi over 4 to pi over 4. And the r we have is cosine of 2 theta, so you square with respect to theta. So going to the identity, so area equals to a half minus pi over 4 and pi over 4. We recall that cosine 2 theta, if it's squared, it's the same as writing it as cosine squared of 2 theta. But there's an identity that says cosine squared of A equals to a half 1 plus cosine of 2A. In this case, my A is 2 theta, so I'll be having cosine squared of 2 theta equals to a half 1 plus cosine of 2 times 2 theta, that's 4 theta. So we have here another half, 1 plus cosine of 4 theta with respect to theta. So we have 1 over 4 outside, and then we integrate from minus pi over 4 to pi over 4, 1 plus cosine of 4 theta with respect to theta. This is the area. So the area finally becomes 1 over 4 integral with theta plus the integral of cosine, it's sine 4 theta. This one you divide by 4. All right, so we have from minus pi over 4 to pi over 4. So if we continue, we find this is pi over 4, then this is pi over 4. So sine over 4 times pi over 4, that's a 0. So we minus. So that's the f at A minus. Then the other one is we factor out theta, so we get another minus pi over 4. And then this one, when it goes here, we get sine 4 times pi over 4, again, another 0. So we get pi over 4 minus, that's plus. So the answer becomes 1 over 4 with pi over 2. Because it's a quarter plus a quarter. You get answer as pi over 8. That's the end of the first session of the Calculus 2 Exam 2 review.